When we think about the mechanism by which this heat is actually transferred, there are actually three ways that energy can be transferred by heat from one place to another. Conduction is the first one, and the one we think about probably the most often. It's the easiest one maybe to understand. Conduction is energy flow between the system and the surroundings that are in direct contact with each other. Conduction happens at the speed of sound because it's really just particles vibrating against each other and a sort of a wave of particle motion, which is what sound is. So heat transfer through conduction is really the transfer of something very much like sound. Let's think about the mechanisms of this and how we can maybe quantify something about it. Imagine that you have a wall here, and this wall separates the outside where the temperature is low, let's say it's winter time, and the inside where the temperature is high because it's been heated. Now energy, Q, is going to transfer itself through this wall to the outside. How fast it does that, we could call that the rate of energy transfer, R for short. Rate is going to be equal to Q divided by the change in time. How much energy over how much time? How fast does energy flow? What things does it depend on? Well, rate is going to be directly proportional to the difference in temperature between the hot temperature and the cold temperature. If it's really cold outside, you're going to lose heat faster. If it's really fairly warm outside, you're going to lose energy at a slower rate. And everybody who pays a heating bill knows this. When it's cold outside, it costs more to heat your house. That's called the temperature gradient. Another thing that it's going to depend on is the area of this wall, the length times the width. How big is the area? The bigger this wall is, obviously, the more energy is going to be lost because the more places there are for particles to begin these vibrations all around this wall, that'll transfer energy to the outside. So bigger area, more energy transferred per unit time. Also, this rate is going to be inversely proportional to the length, the path length through the wall. So if you imagine this wall, like any real wall, having some thickness, and we're going to call that thickness L, the thicker that wall is, well, the slower the energy is going to be transferred through there. This is why in modern houses, walls are usually 2x6 construction because that's thicker than in the old days, 2x4 construction. So if you put these things together, we can get a sort of a law for conduction of heat transfer. Rate is going to be equal to a constant number times the temperature difference and times the area, because it's directly proportional to those two, and divided by the path length. So this law for rate of heat conduction could be used to solve a variety of problems. That K value is called the thermal conductivity for the boundary material, and here are a bunch of K values. You can see they range from fairly small numbers up to fairly large numbers. And here are the units. Milliwatts, well that's thousands of joules per second, thousands of watts, divided by centimeters times Kelvin, which seems like a kind of a strange unit, but we'll see in an example problem why it works out. Here is the example problem. It says in one 24-hour period, how much energy will be conducted through a 16-foot by 8-foot wall that's insulated with 6 inches of fiberglass insulation if it's 21 degrees inside the house and negative 32 degrees outside. Well, first of all, just from the definition, the rate is equal to Q divided by time. And we're interested in knowing how much energy is lost, so we'll solve for that. Q is equal to rate then times the change in time. But R, for conduction heat transfer, which is what's happening through this wall, is K times A times delta T divided by L. So substituting this stuff in for R up there, we get an equation for Q. Q is equal to K times A times delta temperature times delta T time divided by the path length. Now let's plug our numbers in here just without thinking about units at first and see how things are going to work out. If I have 0.4 milliwatts per centimeter Kelvin, which is for glass wool, that's the thermal conductivity, times area, well the area is going to be 16 feet by 8 feet, so that would be square feet, times the temperature difference, well that's going to be 21 degrees C minus a negative 32 degrees C, times time, 24 hours, divided by the path length. It said this was a 6-inch wall. I could evaluate Q, but my units aren't going to work out very nicely. Let's take a look at those units and just looking only at the units. Milliwatts is thousandths of joules per second. So let's just use joules per second and deal with the 10 to the minus third part later. So this is joules per second, that's watts. And then we have down here centimeters, and then kelvins. And then we're multiplying by square feet in the top, and then times degrees Celsius, and then times hours. And then in the bottom we've got inches. What would have to change for these units to work out right? Well, for one thing, if this were in centimeters, then I'd have square centimeters on the bottom. And if this were in square centimeters, then I'd have square centimeters on the top, and that would cancel. And what I'm solving for here is Q, which I want to be in joules. That's my target here. Well, we're talking about a temperature difference, so degrees C really could be kelvins. It's the same thing. Kelvins would then cancel out. And then if hours were converted to seconds, the seconds would cancel out, and I'd be left with joules. So let's do that. First of all, I want my area to be in square centimeters. So I'll take 16 feet, and I'm going to change that to centimeters. There are 12 inches in every foot, and there are 2.54 centimeters in every inch. I will get centimeters. Well, that's 488 centimeters. And 8 feet is the other dimension, so that'd just be half of that. So 8 feet converts to 244 centimeters. So the area of our wall is going to be equal to 488 centimeters by 244 centimeters, and that area is just 119,000 square centimeters. And let's get delta T here. Delta temperature is 21 degrees C minus a negative 32 degrees C. Well, that comes out to be a 53 degrees C or 53 Kelvin temperature difference. So there's area, there's delta T. Let's get the length. Length was 6 inches, and every 1 inch is 2.54 centimeters. So that means our path length is 15.24 centimeters, so that's L. And then the only other thing we have to convert is delta T. Delta T is 24 hours, and we know that an hour is 3,600 seconds. So we can convert there, and we come out with 86,400. All right, so taking all these numbers and plugging them back into that original equation for Q, remember Q was equal to K, A, delta big T times delta time divided by length. Well, the K was 0.4 milliwatts. So 0.4 times 10 to the negative third joules per second times area. Well, our area was 119,000 square centimeters times delta T. Well, that was 53 kelvins times delta time. That's 86,400 seconds. And that's all going to be divided by the path length, which was 15.24 centimeters. Well, this unit, I forgot, included also centimeters and kelvins. So what's going to happen here? Seconds are going to drop out as we predicted. Kelvins will drop out. Centimeters squared drop out, and we end up with units of joules. So Q ends up being equal to 1.43 times 10 to the 7th joules. Another way that heat is transferred is through convection. Now in convection, what's not happening is you have energy being transferred by direct contact. Instead, material actually moves from the system to the surroundings, and with it goes the energy that's stored in its motion of its particles. So here's an example. Say you have a spoonful of soup, and it's too hot. So you got this soup, it's got way too much energy in it. You can transfer some heat away by just taking the warm air above here and blowing on it, providing force, and you blow that air away, and with the air comes the energy that was stored in the motion of that air. And that cools the air up here, which allows more conduction heat transfer out of the soup. And then you blow on it again, you blow Q away. So that's convection. Another form of heat transfer is radiation heat transfer. Now, convection heat transfer happens at the speed that you can move the material. Conduction heat transfer happens at the speed of sound, but because this is really light, or electromagnetic energy that's like light, it means that radiation heat transfer happens fastest of all. The rate at which energy flows for radiation heat transfer is given here in power per unit of surface area. Power is really energy per second. So it's a fairly useful unit. So the power per unit area is equal to, here's the equation, E, a number called the thermal emissivity. It's different for every substance. And it varies between small numbers. E will be 0 for substances that are very shiny, and E can be up to 1 for substances that are pure black. And so real E's are going to be somewhere in between. So that number varies, but it depends on the radiating surface, times a number called the Stefan-Boltzmann constant, sigma, and that number is quantified as 5.67 times 10 to the negative 8th watts per square meter per Kelvin to the 4th power. That's the Stefan-Boltzmann constant. Then that's going to be multiplied by the temperature, absolute temperature of the emitting surface raised to the 4th power. And this will tell you how much energy gets transferred per unit time per unit surface area. Like, for example, this one. An athlete is sitting unclothed in a locker room. The locker room walls are dark and they're 15 degrees C. What's the rate of heat loss by radiation if skin temperature is 34 degrees C and the thermal emissivity of the person's skin is 0.70 if the surface area of the body is 1.5 square meters? Well, let's start out with our equation that quantifies this. Radiative power is going to be equal to the thermal emissivity times the Stefan-Boltzmann constant times the temperature of the radiating surface raised to the 4th power. So let's plug our numbers in here. The emissivity of this person's skin, it says, is 0.70. That's a unitless number, emissivity. And then multiply by the Stefan-Boltzmann constant. That's 5.67 times 10 to the minus 8th watts per square meter per Kelvin to the 4th. And then we're going to multiply by the temperature raised to the 4th power. Well, the temperature has to be in absolute terms. That has to be kelvins. So the person's skin was at 34 degrees C. We'll add 273 to that to get a Kelvin temperature. This gives us 307 kelvins. So that's what goes up here, 307 kelvins. And then we're going to raise that to the 4th power. Kelvins to the 4th are going to drop out. And we're going to end up with power in watts per square meter. It's watts per surface area. The numerical answer is 353 watts per square meter. Well, that's not really what we wanted. What we wanted to know was what was the rate of energy transfer from this person total. So we could take the 353 watts per square meter and multiply by this person's square area here, which was 1.5 square meters, it said the person's body was. And so we end up with 529 watts. So that means every second 529 joules would be transferred away from this person's body. And so they would cool off. Here's another problem. This is more of a thinking problem. It says, say you stop on your way to work and buy coffee to drink when you get to work. So you're going to store this coffee for a little while, and of course it's going to cool off because that's how things work. If you want your coffee to be as hot as possible when you get to work, should you put the cream in when you buy the coffee, or should you wait till you get to work? It turns out that it actually measures. If we took a look at the equation for how fast energy is going to be transferred out of the coffee cup, its power is equal to thermal emissivity times the Stefan-Boltzmann constant times the temperature raised to the 4th power. Now we can make some assumptions here. First of all, let's assume that it doesn't matter when you put the cream. If you put the cream in at the beginning or if you leave it out, the starting temperature is going to be the same. And so that's not a factor. That's a constant, the temperature. Stefan-Boltzmann constant is, well, it's a constant by definition. So the thing that's going to matter here is what's the thermal emissivity. For black coffee, which is pretty dark, it's going to be close to 1 thermal emissivity would be. But if you put cream in there, well, cream lightens it, and it's going to make its thermal emissivity something less than 1. It's closer to shiny, actually. If you put the cream in, the rate of energy transfer is actually going to be lower than if you leave it black. So better off to put the cream in. That'll keep your coffee warmer longer.